Alright, guys. First actual topic, number systems. So we have more than just our usual 0 to 9 or 1 to 10 number system in the world of computer science and math too, really. So we're just going to be covering binary, octal, and hexadecimal because that's the only number system that C supports out of the box. Before we start, why do we have different number systems? Why do we have different ways of representing the same value? Right? Binary, a really straightforward answer. I'm sure you've all heard like binary 0 and 1. That's what the computer knows. I'm sure even the non-CS people have heard the statement. So that's a straightforward answer of why base 2. Computers speak in base 2. Fine. Octal and hexadecimal. Basically, binary gets really large to look at for even rather small values, right? Essentially, you have smaller values, 0 and 1, as opposed to 0 through 9, to represent the same actual quantity, right? So you need more digits or bits to represent the same quantity. So we have octal and hexadecimal to just compress that information. You might ask why not base 10, right? Again, very similar answer, base 8 and base 16. What do they have in common? They're both powers of 2, 2 power 3 and 2 power 4 respectively. Powers of 2 are easy to deal with for computers for the same reason base 2 is easy for computers, right? So, what does base x mean? So, if you guys can just jog your memory and go back to first grade math or second grade or UKG or whatever, whenever you learned it, I don't remember either. You might have, you might remember a concept called face value and place value. So the face value is the value of a digit. That's always going to be 0 through 9 for base 10, right? And then the place value, the units place, the tens place, the hundreds place, that's going to change depending on where it is in the number. So base x just expands on that concept. So base dictates the number of digits or bits or octets or hextets or whatever you want to call it that can be used, right? So base 10, you can use 10 digits, 0 through 9. Base 2, you can use 0 or 1, 2. Base 8, 0 through 7, 8. Base 16, 0 through 9, and A to F, where A is 10 and F is 15. Everything is sequential. So that's 0 to 9, 10, plus 10 to 15, 6, a total of 16. So base X has X possible face values. And each face value's place value is going to be a power of X. So let's take an example in decimal to see what I mean. So here we have taken 345. So this is 5 into 10 power 0, the units place. 5 into 10 power 1, sorry, 4 into 10 power 1. And then 3 into 10 squared, right? This is gonna be 3 into 10 square plus 4 into 10 plus 5 into 10 power 0, which is 1. So 300 plus 40 plus 5, 345. So just take the same concept, apply it to the other bases. Your digits are restricted to 0 and 1, 0 through 7 and so on for each base. And then the place value is dependent on the power of the base. So for decimal, it's base 10, it's 10 power something. Similarly, it's 2 power something, 8 power something, and 16 power something, right? Here I've taken 1011. So 1 into 2 power 3, 0 into 2 power 2, 1 into 2 power 1, and 1 into 2 power 0. 8 plus 0 plus 2 plus 1 is 11, right? And then octal, same thing. 2 into 8 power 1 plus 7 into 8 power 0 is 27 in octal, which is 16 plus 7 and 23 in decimal, right? And then hexadecimal. 1A3 would be 1 into 16 square, A into 16 power 1, which is actually 10 into 16 because A is 10, right? And then 3 into 16 power 0. So 256 plus 160 plus 3, which is 419. And then conversions. Decimal to binary. Again, just touching on it because you'll learn this in DD. To convert 30 into binary, you just divide by 2, take the remainder, and then divide the quotient by 2 again. 3, take the remainder, divide the quotient by 2 again. 1, take the remainder 1, 1 by 2, and then 0, remainder 1. And then you take all the remainders, which is 1, 1, 0, and 1. So 1, 1, 0, 1. Right. Binary to decimal, we already discussed. That's just the place value, face value thing. Decimal to hexadecimal. Same concept as decimal to binary. Except instead of dividing by 2, you divide by 16. You divide by 16, keep track of the remainder, take the quotient, divide by 16, repeat until you get to 0, read the remainders in reverse, and you have the conversion. So 254. 254 by 16 gives us 15 and remainder E, 14, which is E. And then 15 by 16 is 0, and then remainder of F, which is 15. So F, E is our converted hexadecimal number, which equals 254, right? Hexadecimal to decimal, again, same thing, face value, place value. Binary to hex, really simple, create groups of 4. Why? 2 power 4 is 16. Binary is 2. Hexadecimal is 2 power 4, which is 16. So a group of 4 bits equals 1 hexadecimal digit, right? So let's say 11011110. Create groups of 4, and each of those groups is going to be converted into hex, and then D in hexadecimal is our final result, right? Hexadecimal to binary, exact same process in reverse. Each hexadecimal digit is going to be split into 4 bits. So 2 in binary is going to be 0010, and then F in binary 1111, and then write them in order. So 0010 and then 1111. That's going to give you the equivalent binary, right? Binary octal, same concept as hexadecimal, except 8 is 2 power 3 instead of 2 power 4. You make groups of 3 and split into groups of 3. And the other conversions, you can just convert to decimal and then go to the desired base. Though I think I've covered everything actually. Representing negative numbers. Just quickly glossing over it. C just uses 2's complement. The other 2 stuff is just there for your information. So, sign magnitude. Just take the number as is and add 1 extra bit at the very left, denoting the sign. 1 if it's negative, 0 if it's positive. So 5 would be this thing, right? And then minus 5 would be the same thing, but the leftmost bit is 1. The leftmost bit is called the most significant bit because it has the most value in terms of place value. So in the decimal, you could say the leftmost digit is the most significant digit, right? And then 1's complement. You just take the normal positive representation and then flip all the bits. So you have plus 5, and then you turn all the zeros to 1s and 1 to zeros. That gives you the negative representation. One thing common between all three of these representations is the most significant bit tells you if a number is positive or negative. And 2's complement. 2's complement is very similar to 1's complement. You just take the 1's complement and add 1 to it. Right. Why? This has a few advantages over just using plain 1's complement or sign magnitude for that matter. Right. 1. It simplifies arithmetic operations. because you don't have to deal with the MSB. You don't have to see if a number is positive or negative. You can just use the same addition algorithm for both positive and negative numbers and it will just work. Both sine magnitude and 1's complement have two representations of 0, one positive and one negative. So you could have something all zeros like this, which would imply it's a positive 0, and then you could have a leading 1 and then a bunch of zeros, which would imply it's a negative 0 because this leading 1 says something is negative, right? So 2's complement doesn't have that problem. 2's complement has a singular representation of 0, which is all zeros. And any other thing is either positive or negative. You can just look at the sign and tell, the sign bit and tell, right? Third, it allows for easier overflow detection. What even is an overflow? So we don't have infinite storage space to store a number. Say we're working with 8 bits, right? With 8 bits, if we are storing in 2's complement, the very maximum value you can store is this, which is 127. And then if you try to add 1 to it, logically, we should get 128, right? But if you see here, you can try adding 1. This will become 0, 1, 0, and so on. And everything will become 0, and it will just get the 1 at the very leading bit, which is minus 128, and not positive 128, which is the actual answer. So what we're seeing here is an overflow. From the very highest value range can represent, in this case 8 bits with 127 specifically. If you try to add 1 to it, or any number to it actually, any positive number added to the maximum will cause an overflow because it cannot represent any higher numbers, and the carry works in such a way that the MSB flips, right? So it goes from 0 to 1. So from the highest value, it wraps around to the very lowest value. That's an overflow. Okay guys, that's it for number systems. Just a brief overview and we're done. See you in the next video.